The BRE was a lot more positive about powered systems, and they concluded in that way. Suitably designed mechanical systems, which is systems powered by fans, can provide protection to the stair that is resilient to adverse wind and building stack effects. So we wipe the problem out right away. This can be achieved by either depressurising the stair lobby relative to the stair, depressurising the corridor and lobby relative to the stair, or by pressurising the stair relative to the common corridor. And by careful design, mechanical methods can provide a degree of smoke control in the common corridors and lobbies. So they've identified two mechanical methods there. One is ventilation and depressurisation, and the other is pressurisation. So we'll look at them two now in the same way. This is ventilation, and basically what we've done here is to replace the natural vents with fans, whether at the end of the corridors or from the lobbies. If we have a smoke shaft there, now that smoke shaft, because we've got a fan, doesn't have to be 1.5 square metres in area. Probably something less than half a square metre will be more than adequate. And that might be manageable in an existing building. Once again, as the BRE said, the object of the system is to keep the stair, the vertical part of the escape route, free from smoke. Smoke will go into the corridors and lobbies, but as I can set the fan discharge rate, I've got that under my control, I can at least provide a degree of dilution of the smoke in the corridors and lobbies, so people will might be able to see as they're trying to escape, even if they can't breathe. But that is an improvement on the natural systems. Thank you. Pressurisation is the only system where the object of the design is to keep the smoke out of the escape routes. It's used extensively throughout industry for that purpose. And indeed, it is the system of choice in many high-rise buildings overseas, and indeed in many prestige buildings in this country. Many of the very high-rise buildings down on Docklands have their escape routes protected by pressurisation systems. And the most exciting application I think we have in this country is in the Channel Tunnel, where the service tunnel, which runs down the middle of the two running tunnels, is pressurised to actually prevent smoke from a train fire entering that tunnel and contaminating it with smoke. And I learned, Tony, last month from Paul Wendham, the engineering director of Woods, that system is powered by Flightwood's fans, which is quite a convenient thing, Paul. Thanks. The scientific basis for the design of a pressurisation system is contained in this document here, Fire Research Station Test Note 958, which was published back in the early 70s. And that formed the basis for the first code of practice in the UK for the design of pressurisation systems, 5588 Part 4, and indeed has formed the basis of the European standard on pressurisation, EN 12101 Part 6. The interesting thing, what happens when you go from science through all these changes in regulations, for sure it will become more complicated, more difficult to use, and more expensive to use. And basically that's what's happened. Absolutely nothing wrong with the European standard. It's perfectly safe if you've got a pocket like the Sheikh of Abu Dhabi. You know, there's nothing wrong with it. But for simple buildings like this, it gets too complicated. Pressurisation is pure fan engineering technology. And when you start to design any fan system, as a fan engineer, the first thing you have to you need to know is what volume of air do I need that system to move to make it work. With pressurisation, there is an earlier question, and that is what pressure do I require to keep the smoke in the fire room and out of the escape routes. And this this paper, this work gave us that information. Hobson and Stewart gave us that information. And what they actually gave us was a maximum and minimum. The maximum, you can see that the design pressure we require varies with the height of the building. And the maximum goes up to 38 pascals and was based on very extreme weather conditions in the UK. Outside temperatures down to minus 10 degrees Celsius, wind speeds up to 20 metres per second. But it was that maximum which was condensed to give us the 50 pascals design pressure, which is contained in all our codes of practice. But it was a very extreme condition. And Hobson and Stewart gave us a minimum condition for the UK, which is on the left-hand side of that table, which shows you that for a building, let's say, of 50 metres high, and most high-rise residential buildings are not a lot more than that. In the UK, in just over 90% of all weather conditions, 10 pascals would be enough to hold back the smoke from a fire. Hobson and Stewart then went on to look at what happens in horizontal escape routes. And in horizontal escape routes, that design pressure in vertical escape routes, it is actually made up of three things. One is the pressure being created by the fire, one is the stack effect on the building, and the other is the wind effect on the building. When you go into horizontal escape routes, you don't have stack effect, and that disappears. And indeed, on buildings up to 50 metres high, you have very little wind effect. So you finish up just with dealing with the pressure being created by the fire, and that's about 8 pascals. So in an horizontal escape route, running down a corridor, for example, a design pressure of somewhere between 10 and 15 pascals would be all right. That would hold back smoke from a fire in a flat behind the closed door for long enough to allow the people in the other flats to get out to escape.